Okay, Chapter 5, Section 3, the Fundamental Theorem of Calculus. Let's begin by doing a quick overview of some of the big concepts we've covered so far. We started back in Chapter 2 with thinking about the derivative. So over here we'll put the derivative. We did some work there, and then later on, more recently, we started thinking about the area problem. Okay, so let me zoom into the derivative for a little bit. Okay, the derivative. In the question about the derivative, we were looking at things like this. If we had a function x, y, and some function that maybe did this kind of thing, let's say, and we use x way too much. I want to save my x. So I'm just going to use f of t. So let's call this the t-axis. T-axis, it's the independent variable. And so that means that this would be some function f of t. And let's say f of t is continuous on a set from a to b. I don't know, so let's say this is a to b. So this is the little zone we're interested in. And for the derivative problem, we were interested in the instantaneous rate of change, right? That was the big question. What's the instantaneous rate of change? So if we selected some value here, I don't know, c, and that evaluates to some value f of c, like that. Where is it heading after that, right? Is it this is the exact output at c, but where is it heading after that? So for that, we introduced this idea of the tangent line, right? So this is the tangent line, And the tangent line at, well, it's at x equals to c. At x equals, at t equals c. Here I go with my x. At t equals to c. And then what's the slope of that line, right? So the slope of the tangent line, well, that's what this derivative thing was about. The slope is equal to the derivative of the function f at c. Derivative of function f of t at t equals to c. And that'll give me the slope of the line tangent at that point. And that slope of the line tangent at that point would be a way of answering this question: what's the instantaneous rate of change? Okay, so the notation we developed is as follows. So if we have f of t, then we said that the derivative with respect to the t variable of the function f of t is equal to, and then we also developed this little tick mark notation, f of t like that, in general. So now let's put it at c. So let's say that it's at c, at a point c. So the derivative at that point c. And then we develop this limit definition, the limit as h goes to 0 of, and then this is f of, and then it'll be c plus h minus f of c all over h, right? So this was our definition for the derivative of the function at c. So formally we use x. It's perfectly okay to use x. We just use x way too much, and I want to save it. But you might remember it with an x there, f of derivative with respect to the x-axis, put an x there, right? So we might have seen it this way before. ddx of f of x equals to f prime of x, which is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so the x is a dummy variable. It doesn't have to be x, could be any variable. So I chose to use c here just because I'm saving my x. But this might look more familiar. So that's what we did with derivatives. At first, we had to find derivatives the long way with these limits, and that was painful. But then very soon after that, we developed all kinds of great shortcuts and rules that helped us find derivatives quickly. So we didn't have to do it this way for too long. So as a quick little example, for example, if f of x was just the simple polynomial 3x to the 4th power plus 2x plus 7, simple little polynomial, we learned pretty quickly that the derivative with respect to x of f of x would be equal to 12x to the 3rd power plus 2 and then 0 for that one. And then another, right, so another notational style for this would be to just say that it's f prime of x equals to 12x cubed plus 2. Okay, so we learned how to take derivatives. And then later, after we worked with derivatives and found all kinds of great derivatives and shortcuts for derivatives, then we thought about this idea of finding the opposite of a derivative, finding antiderivatives. Antiderivatives. So in other words, if we start here, right, this is what's given, and then we're asked to find the derivative, then we go this way, and this is the answer. Derivative, question mark, find the derivative, and then here's the answer. On the other hand, we could start here. They could give me this one and ask me to go backwards. Start here and go, okay, go backwards and get that way. Find a function whose derivative equals to this, so undo the derivative. That's the antiderivative. Antiderivative. Okay, so as usual with math, you learn how to do something in one direction, then soon enough someone's going to ask you to learn how to do it the other way, how to undo it, right? How to reverse the process. So in an antiderivative question, you might be given this, given 12x cubed plus 2, find the antiderivative, and then we do some work, and then find the antiderivative, find an antiderivative. Okay, and then that's how we would go backwards and hopefully get to this point. We go, okay, well look, if we take the derivative of this function, we get that one. Okay, of course, we also learned that because when we take the derivative of 7 is 0, then someone could easily move that 7 and make it be something else, like this one. The derivative of this one is also 12x cubed plus 2. And so is the derivative of, well, we can even make this a minus 3. The derivative of this is equal to that. So in fact, the constant out here could be anything. So really we just depict it by saying plus c, where c is any number, is the most general type of antiderivative. So this is the general answer. And then we can find specific antiderivatives by choosing c to be any value at all. This constant could be a 7, or it could be any other constant at all. If we're going to choose any constant we want, then c equal to 0 is the most popular answer. Good? Okay, so that was all about derivatives. And we worked with derivatives for quite a while. We're happy with derivatives. And just when we were feeling really nice and solid and comfortable with derivatives, going forwards, going backwards, then all of a sudden we kind of switched gears into something that seems completely different and unrelated, it seems unrelated. We'll see how they're related here. So then we switched over to something called the area problem. So in the area problem, we thought, okay, what if we had a function that looked like this. We have some y there, and again, I want to save the x. So let's make that the t-axis again. And let's say we had some function here, like that. I don't know, some f of t. Let's just make some nice assumptions about f of t. So let's say f of t is smooth, continuous. So this is f of t given f of t is continuous on AB. And just so that the picture looks nice, let's also assume that f of t is strictly greater than 0. So it's above the t-axis, just the way I drew it. Okay, so then we'd have a section, let's say from A to B, like this, and we're interested in the area that's trapped between these guys here. Right, so let me highlight it. So the area problem is interested in finding this shaded region right in here. And the way we did it is to come up with approximating rectangles. That's the first approach we had. Let's do some approximating rectangles. We're going to find the limit as n goes to infinity, because we're going to do n rectangles, of the Riemann sum as I ranges from 1 to n. And now we're going to have f of t sub i's delta t's. Again, you might recall as this using the variable x. So the limit as n goes to infinity of the limit as I goes from 1 to n of f of x sub I delta x. But again, we're using x way too much, and there's nothing special about x. So I'm just trying to switch it up, and also because I'm about to use x for something else. Just as I complain that we use x too much, I'm saving it because I want to use it. This represents the sum of n rectangles, right? So we're going to come up here to our desired area. We're going to break this up into x sub 1, x sub 2, dot, 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 right? So the first one being x sub naught equals a, and the last one being x sub n equals b. And then somewhere in the middle will be that x sub ith value. And then right before it will be the x sub I minus 1 value. All of these are going to have a delta. Oh, here I go using my x's again. So let me restate that. So saving the x's, we're going to use t's. So this would be t sub 1 value there, t sub 2 value there, dot, dot, dot. The very last one would be t sub n value. And the very first one would be t sub naught value, right? Same thing as using an x, we're using the letter t. Somewhere in the middle, we'll have the t sub ith value. And then right before that will be the t sub I minus 1 value. Okay, and then what we're going to do is think about the delta t. Delta t, this is where delta t, we use the equation b minus a divided by n, right? This tells us the width of each one of these rectangles. So the width is supposed to be the same. They don't quite look the same here, but they are. So this little width here is supposed to be a delta t, and it's supposed to be the same for all of them. So this one's also a width of delta t. And then what we're going to do is we're going to come in here and do rectangles. Draw, insert a rectangle. I want to insert a rectangle right there, and it's going to come up. And then we thought about, well, how tall do we make it? Do we use the right end rule? Do we use the left end rule? Do we use the middle rule? Right? So there will be some sort of rectangle, and its height will be established by some sort of point in the base of that rectangle. So, for instance, maybe I decide that this point there ends up being the point that I choose to decide the height of the rectangle. And as long as that point is in that base, then it works out. So maybe I choose the point t sub I star, which is a value within there. Okay, so at first we let this be some t sub I star value such that t sub I star is a member of, is an element of the set, which is the set between t sub I minus 1 all the way out to t sub I. Okay, so that's how we initially described it. And then we noticed that the t sub i's make a sample, right? So let me get rid of this notation here. We don't need it. So then we created a sample set. Set t sub star sub 1, t sub 2 star, t sub 3 star, dot, 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 all the way out to t sub n star. So this is a sample set where t sub 1 star is a value in this first rectangle. It's a random value somewhere in that base. T sub 2 star is a random value in the second rectangle, and so on and so forth. Okay, for more detail, look at the previous video. But the point was that it could be any sample value, so and then as the limit as n goes to infinity, eventually we say, well, all of them, no matter what choice you make, are going to give you the same answer. So why not use a simple choice? And the simple choice we decided on is just to use the right-hand rule, which is just to leave it as a t sub I. Okay, so that's a quick review of everything from the previous couple of sections. We don't really need it here, so I'm just going to erase this whole thing right here, back up a little bit, and say that, okay, let's get rid of the star part of it there. And so I'll leave that t there. And so this is where the t sub I, so t sub 1, t sub 2, dot, 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 somewhere in the middle is the t sub I, dot, 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 and we end with the t sub n. Okay, these are the sample values that determine the height of each rectangle. Sample values in the set from A to B that establish the height of each rectangle, right? Such that f of t sub 1 is the height of the first rectangle, and then f of t sub 2 is the height of the second rectangle. F of t sub 2 is the height of the second rectangle. And then dot, 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 dot. So that means that f of t sub I is the height of the ith rectangle. Okay, so this will give us the area we're interested in. First, we break up our region from A to B into n approximating rectangles, where each one has a base of delta t defined by this formula, and each one of them has a height, each rectangle has a height described by this little notation here. So this is the sum of the first n rectangles, and then we let n go to infinity, and then we defined a new notation for this called the definite integral. So this is equal to the integral from A to B of f of t dt. This is exactly equal to that. Okay, so we have this area question, and seemingly it looks like it's very different from the question of derivatives. Okay, so we had the derivative problem, instantaneous rate of change. We defined derivatives using this sort of limit definition. We knew how to take derivatives using the limit definition. Then we found a bunch of shortcuts that helped us find derivatives quite easily. And then once we're happy finding derivatives Then we thought about going in reverse and finding antiderivatives. So we're all pretty happy with derivatives. Then all of a sudden we switched gears into this seemingly new idea called the area problem. So now we're interested in the area that is trapped between the function, f of t in this case, and the t-axis, between t equals to a and t equals to b. We initially did it by coming up with approximating rectangles and then finding the limit as n goes to infinity of those n rectangles. Right, so this is definitely not an easy way of finding that area, but we worked with it. Okay, so the fundamental theorem of calculus is a way of connecting all of these ideas. They look like they're separate, they have nothing to do with each other, but the theorem allows us to connect them all together and see that they're two sides of the same coin. Okay, so let's see what the fundamental theorem of calculus says. So the fundamental theorem of calculus comes in two parts. For the first part, we need to define a function this way. So let's define the function g of x to be equal to the integral from a to x of f of t dt. Okay, this is where f is a continuous function on a and b, a to b, and x varies between a and b. Observe that g depends only on x, right? So the function g is a function of x, which appears as the variable in the upper limit of the integral. Right? So the variable is this x value right there. It's tempting to think that this f of t dt, that this is some sort of a variable here, but it's not. Remember what this is defining to be. This is defining to be as, this results, let's go back to the limit definition. This results as the limit as n goes to infinity of the Riemann sum as I goes from 1 to n of, and then this would be f of t sub I, and then we need a delta t, where delta t is the region, right? So this is where delta t would be equal to x minus a over n, right? So we need a little width of each rectangle, we need a height of each rectangle, and that's what this represents. So this variable t goes back to being a value in the subset below the function where you're trying to find an area. So just to kind of give a picture, again, if we had some function f of t, and we're trying to go from a to say to x there, well, from a to b, and then let's say x is some value between a and b. So let's say x just goes right up to there. Here's x. So what we're interested in is letting g be the area so far, right? The area so far as x is allowed to move left and right. When we choose a specific value, when we let x equal a number somewhere in here, then we can plug it into there, and then we can find an actual specific answer. There's a specific area when this variable is selected. But if it's allowed to move anywhere between a and b, if it's a variable, then this upper limit of integration becomes the independent variable of this function. And so we have a function g of t described this way, right? So the t is not a variable that you get to choose. The t is, part of breaking this up, right? We're going to break this up into n rectangles, and then the first rectangle is going to have a t sub 1 value in there. The second rectangle is going to have a t sub 2 value in there, dot, 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 dot. So we're going to have t sub n values chosen from the base of each rectangle so that we can do our approximating rectangles. So this isn't a variable that we get to choose. Good? This is a value that helps us establish our n rectangles. Okay, let's take a look at this free online applet to help us visualize this function. There's a lot of stuff going on here, and we'll come back and revisit and really examine all these other details. But for now, let's just focus on a very specific thing. I want to get your eyes to focus on this part here. There's the integral from 0 to 4 on my function x, which is this straight line here, dx. So we know that this, just this right here, should be the area here in blue. Okay, so don't worry about all the other stuff that it's doing. For now, let's just focus on that. And notice that in this particular case, it forms a very easy geometric shape to figure out. Remember, the area of a triangle is 1/2 base times height. The base is 4 units. The height is 4 units. So that would be 4 times 4 times 1/2 gives you 8. And that's what this is right here. So ignore this stuff in the middle for now. We'll come back and visit and see what that means. But for now, the integral from 0 to 4 on the function x dx equals 8, which we can easily confirm geometrically. So if we let this be a definite integral like this, these values are set from 0 to 4. But now what I could do is leave this one alone and then move this top one. So maybe instead of a 4, maybe it comes back down to 2. So now the area between 0 and 2 of x dx, well, again, the formula is 1/2 base times height. So it's 2 times 2. The base is 2, the height is 2. 2 times 2 is 4, times 1/2 is 2. So it's telling me that the answer is 2. Right? So like imagine that I give you a homework problem where I said, find this area, okay, and then you do all this work this way from 0 to 2 x dx, and you figure out that the answer is 2. You can either do that because it's a nice geometric shape, that's the easy way to do it, or the hard way to do it would be to set up that limit as n goes to infinity of n approximating rectangles, and then find that, okay, so that's a lot of work. And then once you finish doing that, I go, okay, well, great, now answer this one. Find this one now. I'm like, okay, it's almost the same. And now it's 0 to 4, x dx. We do a bunch of work, and we see that that's, okay, it's equal to 8. I go, okay, that's fine. Great. Now answer this one. Right? So what am I doing? I'm constantly just changing this number up here. Right? So as you can see, as I change it, I get different values. So this right here is defining a function on this as the independent variable. Now, again, it's unfortunate that we use x for so many things that it would be weird for me to say it's g of x because I'm already using x in there. So it would be nice if this thing had done a different letter in here, like t dt, or if I just define my function out here to be g of w, for instance, where w is my new independent variable, and then this upper limit of integration would be w. But I think I would already lose like half of you if I wrote the g of w. So at any rate, my point here is that the only thing that moves, right, if we focus our attention here from 0 to blank x dx, as I move this, the only thing that changes is this upper limit, and every time I change it, it actually gives me a different answer. So it becomes the independent variable on a new function, right? So the function that describes this area from a fixed initial spot to some value, so here's where the moving x would be, this value here. As it moves, it describes a independent variable, and so we can define a function that way. So here's a nice little graphic that depicts the same thing. Imagine that the x gets to move left and right, right? So as it moves left and right, it'll trap a different amount of blue area. As it goes this way, it traps more blue area. As it goes this way to the left, it traps less blue area. So if we defined that g of x function to be the area in blue, from a to x, that's going to be that g of x function, and it's going to be equal to the integral from a to x, right? That's the independent variable, on this function f of t dt. Good. So remember, t is not an independent variable. T refers to a sample set of values which are used to establish our approximating rectangles. Okay, so this is the independent variable there. Okay, so if we define a function g this way, finally we can come back and see the connection between the area problem and derivatives. So, the fundamental theorem of calculus part 1. If f is continuous on the set from a to b, then the function g defined by g of x equals to the integral from a to x of f of t dt, where x is a value between a and b, is continuous on ab. So this is the g function. That g function is guaranteed to be continuous on the set ab inclusive and differentiable on ab. And here's the important part. The derivative of the g function, so let's say g prime x, which we know is the same thing as saying the derivative with respect to x on g of x, right? Just two different ways of saying the same thing. The derivative of the g function is equal to this, and so this is equal to the derivative with respect to x of, and then, well, the g function was defined this way. It's the integral from a to x of this f of t dt. And here's the nice part. The fundamental theorem of calculus says that these two operations are inverses of each other. They cancel each other out. We learn how to multiply, and then we learn how to divide, and those two operations cancel each other out. We learn how to add, then we learn how to subtract. Those two operations cancel each other out. We learn how to take square roots, then we learn how to take squares. Those two things cancel each other out. And these two are inverse operations of each other. So the derivative of an integral defined this way turns out to just be equal to f of x. Good, which is that function right in here. Well, let's put it in. It's this guy right here. That's what that function is. Good, and we can carry this across and say that the derivative is equal to that, and so the derivative equals to that. Okay, that's what part 1 says, that the derivative of an integral defined this way is equal to this. So the derivative and the integral kind of undo each other. Think of it this way. If we had some function f of x, and we decided to add 3 units to that function, but then we decided to also subtract 3 units, the process of addition and subtraction undo each other, right? They're inverse operations. Inverse operations. So the answer to that is just going to be f of x, right? These two kind of undo each other. Same thing with, say, multiplication and division. If I have some function f of x, and then I decided I wanted to multiply it by 5, and then I decided, well, I also want to divide the whole thing by 5, these two operations undo each other. And again, they are inverse operations of each other. And the answer is just going to be f of x, right? They're inverse operations. Multiplication and division are inverse operations. Addition and subtraction are inverse operations. And now we're saying that taking a derivative and taking an integral from some constant a up to x. Now it gets a little confusing because we have to put some qualifiers on here. But the derivative of an integral f of x, f of t dt is going to be equal to f of x. So in that same style, except there's a few qualifiers. Consider the following, for instance. We also know that if I had 3 squared and then I take the square root of it, well, that's just going to be 3, right? Squaring and square rooting undo each other as well. They're inverse operations of each other. And I can also do like 5 squared and then square rooted. Well, that's also going to give me 5. So it's maybe tempting to go, okay, well, anytime you have a function and then you square that function and then you take the square root of that function, that those two operations undo each other, they're inverses, and then you end up with f of x. And that's kind of true, except we have to make sure that we started off with a positive number. Because consider the following. If we start off with negative 3, start off there, start with negative 3, and then we square -3, and then we take the square root of -3. Squaring it makes it positive, and then square rooting it is going to get me to +3. So I don't end with the same answer, right? Not the same. Not same. So it's not generally true. This isn't always true. It's always true as long as whatever is in here is positive. So this is true if f of x is strictly greater than 0, greater than or equal to 0. If f of x is greater than or equal to 0, then this is true. Yes, these two operations undo each other. We're happy, and it gives us that result. So my point is that sometimes there's sort of qualifiers that have to happen in order for it to be true. Up here, there was no qualifiers. F of x would be anything, and these two operations undo each other. F of x would be anything, and these two things undo each other. Whereas here, not so much. First of all, we had to define it as this way, right? And that's another good point to bring up. Why did we have to define it this way? Well, we just saw from that free online applet that when we had a very specific integral, we had the integral from 0 to 4 on the function x dx. Remember, this is not an independent variable, right? This is a variable being used to establish the heights of our approximating rectangles. So this is the same as the integral from 0 to 4 of t dt. It's just a dummy variable. You can use whatever is your favorite letter. I like to use w. The integral from 0 to 4 of w dw, right? They're all the same. But I know we're used to seeing x. That's fine. So at this point, we can interpret this as the area, right? This has an interpretation as an area. And the function is this one. So it goes like that. It's like the line y equals to x. And we want to go from 0 to 4. And we want to find the area underneath that curvature. So we want to okay, so because it's the line y equals to x, we also know that this must be a 4. And from because it forms a very simple, straightforward geometric shape, then we know that we can easily find that answer, right? We don't need calculus to find that answer there in yellow. We answered this long ago when we first looked at geometry. This is 1/2 base times height, so it's 1/2 times 4 times 4. So we know the answer is 8. Good? Okay. So that means that this integral equals to 8. Let me zoom out a little bit more. That means that the integral from 0 to 4 on the function x dx is equal to 8. So here's a question. What if I try and do the derivative of this? What if I tried to do the derivative with respect to x on the integral from 0 to 4 of x dx? It looks an awful lot like this stuff. It looks an awful lot like this, but not quite, right? So this, the answer is 0, right? Why? Because this isn't a function. This is a constant number. We just established that this is 8. This is the derivative with respect to x on 8, right? That's what this is. And the derivative of any constant is just 0. So it's silly to try and take the derivative of a function defined like that, or sorry, of an integral defined this way of a definite integral. That's why we had to define this new function. We needed to have a function in order to get a derivative, and that's why we defined our function g of x to be equal to the integral from some constant to x on f of t that's why we had to define this function g of x equals to the integral from some constant a to x on f of t dt, so that it's a function on x, and thereby we can take derivatives of it. If it was just a definite integral like it was over here, then the answer would always be 0, and we wouldn't really have any fun. Okay, so These two operations are inverses of each other. They kind of cancel each other out, but there's conditions. There's like things we have to consider. It's not always going to work out. First of all, we have to define it this way, where we have our variable right up here. And remember, this is a dummy variable. This is the real variable. And so the derivative of this entire thing, is equal to that function evaluated at x. That's what the fundamental theorem of calculus tells us. Let's look at an example. For example, you might be asked to find the derivative of this g function, where now they've specifically given us an equation. So they're asking us to find g prime of x, right? Find the derivative of the g function, which we know is the derivative with respect to x of the g of x function, which we know is the derivative with respect to x on the integral from 0 to x on 1 plus t squared dt. And the fundamental theorem of calculus says that these two operations undo each other. And the answer is just this function evaluated at the variable. This just becomes 1 plus x squared. Good. And that's our answer. So g prime of x is just equal to that. Okay, another example. Let y equal to the integral from 0 to x to the power of 4 cosine squared theta d theta. Okay, so it might be tempting to say that this is easy, following the pattern from before, that we would end up with cosine squared of x to the fourth. But we have to be careful that our definition had a variable x, not x to the power of 4 up in the numerator. So this is what we have to do. We're asked to find the derivative, right? So that means we want to find y prime. So y prime is equal to the derivative with respect to x of the y function. So this is y prime equals the derivative with respect to x of the integral from 0 to x to the power of 4 cosine squared theta d theta. Good. And normally they would undo each other if this was just an x there, but it's an x to the fourth power. So I'm going to have to do a u substitution. So let's let u equal to x to the power of 4. So I'll have y prime equals to d dx on the integral from 0 to u on cosine squared theta d theta. And of course, thanks to the chain rule, what we're going to have is as follows. The y prime is going to be equal to cosine squared u, right? That's the first the fundamental theorem of calculus. Part 1 tells us that this is going to be equal to that. Given that this is, well, you know what? Let me write one more step here. That this is equal to the derivative with respect to u on the integral from 0 to u of cosine squared theta d theta times the derivative with respect to x on the u, right? That's the chain rule. So that means that y prime is going to be equal to the cosine squared u times the derivative with respect to x on the u, which was x to the power of 4. And so my final answer is going to be that y prime equals to cosine squared u, where the u was the x to the power of 4, times the derivative of x to the power of 4 is a 4x to the power of 3. So let's just write it over here. Y prime is equal to, and I'll put the 4x to the third power out in front, times cosine squared x to the power of 4. That's my answer. Okay, well, these are fun little problems, but there's only so much you can do with them. So what we really need is the second part, part 2 of the fundamental theorem of calculus. That's where the real work takes place. Okay, back to part 1 of the fundamental theorem of calculus. It states that if we define a function g this way, this g function is equal to this sort of an integral, where the independent variable is this guy up there, the upper limit of integration. Okay, so then defining g this way, when we want to find the derivative of this function, that would be the derivative of the integral. These two operations kind of cancel each other out, and the result is just f of x, where x is that independent variable up there. Okay, so these two operations kind of undo each other. All right, well, the part 2 is going to kind of go in reverse, and that's really the most important one. So part 2 is going to say that if we have the integral from a to b of the derivative with respect to x of, say, some capital F of x function, so that all of this is in the integrand. We're trying to integrate all of this. Dx, of course, dx, right? So here we have the reverse order. This is the integral of a derivative. And again, these two operations kind of undo each other, and the result is going to be this function right here, except with a little bit of a twist. It's going to be equal to that capital F function evaluated at the b minus that capital F function evaluated at the a. Good? That's what that's saying. Another way of describing this is to write it as the integral from a to b on f prime of x dx equals to f of b minus f of a. And yet another way of writing it, I think this is the one your author likes, is to say that the integral from a to b on lowercase f of x dx equals to capital F of b minus f of a, and this is where capital F of x, the derivative of capital F of x, is equal to lowercase f of x. So they're all saying the same thing, but personally I like this one, this presentation, best, because it pits the two operations right next to each other, and we can see that they kind of undo each other. The integral of a derivative is equal to that function, right? Over here they were in the other order. First we take a derivative of, well, I guess first we find an integral, then we take its derivative. Whereas here, first we take a derivative, then we find its integral, or the other way around. So these two operations are kind of switching order from there to there. But in either way, they kind of undo each other, maybe just with a little bit of a twist. Okay? So, for example, let's do an example with this. For example, let's say that capital F of x is given to be x cubed plus 2x plus 7, and you're asked to find the integral from 0 to 1 on the derivative with respect to x of capital F of x dx. Good. So this way. Well, part 2 of the fundamental theorem of calculus says that this integral process and this derivative process kind of undo each other, and that this is going to be equal to just evaluating my function at 1 minus evaluating my function at 0. Makes it super duper easy. And so now this is just going to be something cubed plus 2 times something plus 7 minus something cubed plus 2 times something plus 7, right? Just following the rules for capital F and evaluating it at 1, I get a 1 cubed plus 2 times 1 plus 7. And then evaluating it at 0, I get a 0 there, plus 7. So I get an answer of 1 plus 2 plus 7 makes it 10. So it would be 10 minus 0, 0, minus 7, which gives me a final answer of 3. Good, good, good. Okay, so an equivalent way of asking you the exact same sort of question, just making it a little bit more challenging, let's say, is to go, okay, the derivative of the capital F of x function, d dx of capital F of x, well, that is equal to 3x squared plus 2x. Oops, sorry, plus just 2. Plus 2. This is the derivative, right? So instead of writing it like this, an alternative way that they could present this question is to say, find the integral from 0 to 1 on the derivative with respect to x of, and then kind of spell out the question, x cubed plus 2x plus 7, like this, dx. Remembering that, just to be clear, that this dx applies to this entire function there. So take the derivative of this, and then get an answer, and then integrate it from 0 to 1. Well, it's going to be the same as that. So I know the answer is 3. Done. Put it in black. So I know the answer is 3. Good. Okay, or another alternative question, same thing, would be to say, let's go from 0 to 1, find the integral from 0 to 1 of, and then maybe they just give you the 3x squared plus 2, like this, dx. It's the same thing, right? The derivative of this function is this. It's just already been differentiated, right? We found the derivative. So if I was going to solve this question, then the answer is going to be 3. But in order to figure that out, I'm going to have to take an initial step of rewriting this, right? Rewriting this using my knowledge of antiderivatives. Antiderivatives. So that I can go backwards and figure out that the antiderivative or an antiderivative is equal to x to the power of 3 plus 2x plus c, right? This is the general form of an antiderivative. And then, I've done the proof, but the fundamental theorem of calculus shows that, in fact, when you go backwards to go this way, and then maybe it's not so clear what that c is, right? In this example, it was a 7. But it could be anything when you find the general form of an antiderivative. Turns out it doesn't matter. That they'll cancel each other out and everything works out fine. So if you're given a question like this, step 1 is going to be to find that general antiderivative and then apply it. Okay, let's see what your homework questions look like. Okay, looking at your homework, use part 1 of fundamental theorem. Evaluate the integral. Okay, so this is using part 2 of the fundamental theorem. Let's try problem number 24. Okay, so notice that this is not given to us in the form, the integral from a to x of the derivative with respect to x of some function f of x, like this, dx, right? So in other words, if it had given it to us like this, then we'd know the answer is just this f1. But this isn't given it to us like that. So we have to first of all find the antiderivative of this function and evaluate it like that. So note that the antiderivative, the antiderivative of x to the power of negative 2/3, x to the power of negative 2/3. We're looking for something whose derivative, a function whose derivative equals to that. So we know from our patterns that if to take a derivative, we subtract 1 from the exponent. So to go backwards, we're going to add 1 to the exponent. So put a plus 1 there. Well, plus 1, we need a common denominator, so really let's add a 3 over 3, which gets me to positive 1/3. So this gets me to positive 1/3. And so now if I think about taking the derivative of this function, I bring down the 1/3, subtract 1, so that I get the correct exponent, but then I'd have a 1/3 here. So I need to fix that by multiplying it by 3, or the pattern is to copy that, right? So the pattern would be to do this, 1 divided by 3, where this is the variable there. And then that simplifies, of course, to 3x to the power of 1/3. Okay, so this is the function, let's just label it as an f of x. This is the function f of x such that the derivative with respect to x of this function f of x equals to exactly what we're interested in, the x to the power of -2/3. Now, of course, when we want to think about the antiderivative, there's this idea of a plus constant. Like maybe the derivative of this gives you what I want, but so does this one. What if I have a plus 5 there? Because when I take the derivative of 5 is 0. So there could be a constant there, plus c, plus some c, would give me a function whose derivative equals to that. Okay? All right, so let's come back up here. And now this isn't the way we would always do this. I just want to show you how it matches that. So the integral from 1 to 8 on x to the power of -2/3 becomes the derivative with respect to x of the function x to the -2/3. Wait, I'm sorry. Becomes the derivative of 3 x to the power of positive 1/3, parentheses, and maybe plus some constant, dx, right? So all I did was replace this with this, all of this, including the derivative part. Good, so let's put it in parentheses here. So this derivative is referring to this function, right? As we see over here, the derivative of this function equals to exactly x to the power of -2/3. And now that I have an integral and a derivative right next to each other like this, now it matches this. Now I know that I can use the part 2 of the fundamental theorem of calculus that says that this is going to be equal to f of, this is b here. So this will be f of b minus f of a. Good. So all we have to do is evaluate this function at 3 blank to the power of 3 plus c, and then 3 minus, and then 3 blank to the 1/3 plus c, and let's wrap it around parentheses. That's this one here. That's this function evaluated at 8 minus this function evaluated at 1. So we're going to put an 8 here, and we're going to put a 1 here. And then simplify. This is going to be equal to 3, 8 to the 1/3 power, 3 times 8 to the 1/3 power, plus c, minus 3 times 1 to the 1/3 power, minus c. And now this is why, now it becomes clear why it doesn't matter what c value you choose, they're going to cancel out anyway. So whether you chose c to be 7, to be 2, to be 0, it doesn't matter. They cancel out anyway. So really, in practice, we never really consider the c when we're doing this. We consider the c in the case when we're doing the indefinite integrals, the antiderivatives, but not when we're doing definite integrals. So this will be the last time that I think about this extra c in there. And now all we have to do is simplify this as much as we can. The cube root of 8 is 2, so it'll be 3 times 2 minus 3. So 3 times 2 is 6 minus 3 is equal to 3. Right? So the integral from 1 to 8 on x to the -2/3 dx equals to 3. Okay, we can easily confirm our work using this online graphing applet. we got to type in our equation, which was x to the power of parentheses -2 divided by 3. And we were going from 1 to 8. 1 to 8. And so let's zoom out a little bit. So here's our graph of x to the 2/3 to the -2/3 power. And we wanted to go from 1 to 8, the area trapped above the x-axis below the function x to the -2/3, to the right of 1, but to the left of 8. That would be this area here. Maybe even more zoomed in. There we go. From 1 to 8, above the x-axis, below the function x to the -2/3, between 1 and 8, and we can see that this online graphing calculator automatically gives me the answer of 3, right? Confirming the work we did. Okay, so this is a perfectly good answer, but it's ugly, it's messy. We got to go off to the side and think about antiderivatives. We included this extra c, and then I came back and rewrote my question by rewriting this part here highlighted in yellow with a derivative, the derivative of some function. It's just messy. So we developed a nicer, neater way of answering this question that I think will be useful as the equations get more and more complicated. We need a more sophisticated way of expressing our answer. So we're going to choose to answer it in the following way instead. So we're going to have the same question. Find the integral from 1 to 8 on x to the -2/3 dx. Same question. But instead of going through the trouble of finding the antiderivative off to the side and then rewriting it this way, we can just jump right to stating the antiderivative. And we don't have to worry about that constant. So we would just say that this is 3x to the 1/3 power. Because, right, just kind of thinking to ourselves, because the derivative of this equals to that. Okay, and then we do this notation with a big bar like that, and we say that this means that it's going to get evaluated from 1 to 8. Okay, so this bar here matches these two values there, and this is meant to identify that we're going to evaluate this function 3 blank to the 1/3 power at the 8 minus 3 blank to the 1/3 power at the 1. Right, so we put a 1 here, an 8 there, so it's always the top one goes first, minus the bottom one. And after we simplify all that, we're going to get the same answer, that this equals to 3. Okay, so just a smoother way of depicting the same situation there. Coming up here to the general form, like before, we're just introducing one more step, or writing it in a slightly different way. So I put or, the integral from a to b on a function. So let's say that this function is f of x dx is equal to capital F of x evaluated from a to b, which means that it's equal to capital F evaluated at b minus capital F evaluated at a. Good. So this is a very common way of expressing this question, f of x dx, and this is where, of course, the derivative with respect to x on the capital F equals to the lowercase f of x. Good. Okay, so hopefully it makes sense. And let's try another problem. Okay, how about if we try number 34? Okay, so let me do it with the slightly longer notation style for a couple more times so that we get used to it, and then I'll do it with the shorter, faster notation style. You don't have to do them both ways. I just want to make sure people are following what we're doing. So I'm going to take the time to rewrite this as a function whose derivative equals to this, so that I can have the integral and derivative signs right next to each other. So I'm going to say that this is equal to the integral from 0 to 3 on the derivative with respect to x of. Now, the derivative of function that equals to sine, we know the derivative of cosine equals negative sine, so this would become minus 2 cosine x. The derivative of this is going to be equal to positive 2 sine of x minus, and we know that the derivative of e to the x is just going to be e to the x. So I know that the derivative of this function here, all of this, really is exactly this. So I just reinterpret it like that. And now that the integral and the derivative are right next to each other, it makes more sense to me that they kind of undo each other, and that this then becomes equal to this function evaluated at 3 minus this function evaluated at 0. So this will become minus 2 cosine of blank minus e to the blank minus 2 cosine of blank minus e to the blank, making sure to separate these two functions like this. Be real careful with all those signs. Lots of minuses running around everywhere. So first we evaluate this at 3, put a 3 there, put a 3 there. And next we evaluate this at 0, so put a 0 there, put a 0 there. Okay, so this is just going to be minus 2 cosine of 3. That doesn't really simplify very much. Minus e cubed. Then minus minus becomes plus 2 cosine of 0. And then minus minus becomes plus e to the power of 0. Cosine of 0 equals to 1. And e to the 0 equals to 1. So 0 times, cosine of 0 approaches 1, not 0. Approaches 1. So this will be 2 plus 1 gives you 3. So the whole thing then becomes minus 2 cosine of 3 minus e cubed plus 3. And that's about as simple as it gets if you want to get an exact answer. Otherwise, you can get your calculator and get a nice approximation. But that's good enough for us. So that'll be our answer. Right? And so that's the integral from 0 to 3 on 2 sine x minus e to the x dx equals that. Okay, and then the other slightly less, the other way of writing it without doing this middle step, the other notation style that we want to adopt is this one. The integral from 0 to 3 on 2 sine x minus e to the x dx. Okay, so we're not going to bother with this step of trying to rewrite it. So we're just going to jump right into our antiderivative, which is minus 2 cosine of x minus e to the x. And this is going to get evaluated from 0 to 3. Right? So this function gets evaluated from 0 to 3. So this means that it's exactly that up there. So it's minus 2 cosine of blank minus e to the blank minus 2 cosine of blank minus e to the blank. And again, be real careful to put parentheses where they need to go. There's a lot of minuses running around everywhere. So for this first function, we put a 3 there, put a 3 there. For this one, we put a 0 there, put a 0 there. And just like before, we do a bunch of work here. Just reduces a little bit. And we end up with the same answer of minus 2 cosine of 3 minus e to the third plus 3. Say we're asked to find the integral between negative 2 and positive 1 on the function 1 over x squared dx. Okay, so we got to think about the antiderivative of this guy, something whose derivative is this. So we might want to rewrite it. Okay, so we might want to go, this is the integral from negative 2 to positive 1 on x to the negative 2 power dx. And we know we want to find the antiderivative. We could do it the slightly longer way of kind of coming off to the side and thinking about that antiderivative. So let's see, that would be the same thing as when we take a derivative, we subtract 1, so the reverse would be to add 1. So it has something to do with x to the negative 1. And if I do a guess and check process, when I take the derivative of this function, the derivative with respect to x on this function, well, I would bring the negative 1 out in front, minus 1 times x to the minus 1 minus 1. So it gives me the correct exponent, but then I have this extra lingering negative 1. So that's how I know to introduce an extra negative 1 out in front. Okay, so then I'll have an extra negative 1 out in front. Make a little space here, made this equal sign too big. That means I'll have an extra negative 1 out in front there. Equals. And these are multiplied, not subtracted, so this is negative 1, negative 1. So the negative 1 that I bring down will multiply with this red negative 1, and together they multiply to positive 1. And so the derivative of this function will give me exactly what I wanted, that x to the negative 2 power. Right? This whole thing will then just give me x to the negative 2. Negative 2, where these guys just cancel and become 1. Okay, so the slightly longer notation would be to rewrite this as the derivative of a function whose derivative is this. So this is equal to the integral from negative 2 to 1 on the derivative with respect to x of the function negative 1 times x to the negative 1. Right? We know that the derivative of this is equal to exactly that. So this is being replaced by this dx. Good. And so we know that when we have it in this format, the integral of a derivative, these two operations undo each other. And so we get that this is going to be equal to this function, negative 1 times x to the negative 1, evaluated at, and then we use this notation, negative 2 to 1. Good. Okay, so this middle step is often skipped, right, as we kind of visualize what it is. We will very, very often skip this step, right? In fact, I think I'm one of the few people that ever writes it down. So it's perfectly okay for you to skip it. But if you need it, I think it can be useful at first while you're kind of learning to work with these. Most people skip this step. And as you become more and more comfortable with this process, with this work, you'll skip that too. Right? All I did is I rewrote this as a function whose derivative, right? I found the function whose derivative gives me that. That way I have the integral sign and the derivative sign right next to each other. It helps me. I like it. But you don't have to. You can skip that and go right into the antiderivative. Evaluate it from, in this order. Remember, the order makes a big difference. Okay, and so this notation means that we're going to take our function, evaluate it at one of the top number, minus, and then our function. Now be careful with all these little minus signs. That's really the biggest problem or the biggest issues people have with calculus. All these tiny little minus signs and negatives all over the place, and it's very easy to make a mistake, right? The order makes a big difference, so be very careful. Okay, so first we're going to evaluate this whole thing at 1, so put a 1 there, and then evaluate this whole thing at negative 2, so put a negative 2 there. Okay, so then let's try and simplify this. When we have a negative 1 in the exponent, all that means is we flip it underneath, right? Put it underneath 1. So this becomes negative 1 divided by positive 1, right? Just moving this. In fact, let me put it in color. This green here, this 1 is the 1 from there, to the negative 1, minus, and now likewise, we have a negative 2 to the negative 1 power, so all we have to do is put that underneath. So we end up with negative 1 divided by negative 2. And now we can simplify that. So of course the negative from there and negative from there cancel. And so this whole thing just simplifies as, zoom out. This whole thing just simplifies as -1 minus a half. So getting a common denominator of 2 over 2, this gives me that this is going to be -2 minus 1 gives me -3 over 2 as a fraction, or -1.5 as a mixed number, right? And on the left-hand side, all the way down to here is this integral. So we're saying that the integral from -2 to +1 on the function 1 over x squared dx is equal to this number. So that's what we get, right? And then at every step there, this is also the same integral from -2 to 1 on 1 over x squared dx, right? And dot, 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 dot. So I'll just put same on the left-hand side. Everything stays the same. Copy, copy all the way down until you get to that. Okay, so we did beautiful work. We figured out how to rewrite it this way. We found the antiderivative. So that looks really nice. And again, this step right here, you can step. Most people skip it, and that's fine. And I expect you to learn how to skip it or be comfortable skipping it after a little bit of practice, because it's just kind of cumbersome. It's one extra step you don't necessarily need to write down. Should be something you can do in your head. So almost everyone just skips that step and goes right over to the next one, which is just to write down the antiderivative, the general antiderivative. And remember, this is with c equals to 0, since the constant doesn't matter, as we saw in a previous example. Okay, then we evaluated at 1, evaluated at -2. So this is a wonderful application of our whole integral system. Everything is wonderful. Too bad it is all wrong. Sorry. Why is it wrong, right? This is not true. Let's make sure that you don't leave that in your notes. What's wrong with it? Well, what's wrong with it is that we didn't pay attention to the conditions of how this whole thing works out. To see why it's wrong, let's take a second look at the fundamental theorem of calculus part 2 and see if we've satisfied the conditions. Okay, coming back to our fundamental theorem of calculus, part 2, this is the one we're using. Notice that the condition is that if f is continuous on AB, then it must be true that, okay, so then we use everything. But the equation we were just looking at is not continuous on that interval, right? Let's graph it. Okay, using Desmos, I can type in f of x equals to 1 divided by x to the second power. And I don't want to use red. Let's use blue. There's our function, and if we look at our integral, remember this is the area underneath this function above the x-axis, trapped between -2 and 1, right? So here is -2 all the way out to 1, somewhere right there. That's the area underneath this function above the x-axis. If we shade it in, okay, let me copy that. Okay, so the integral from -2 to +1 on the function 1 over x squared dx. Okay, so this blue one here, this blue function is the function f of x equals to 1 over x squared, right? Both sides of it. And we can see that this is heading off toward infinity. There's a vertical asymptote at 0, right? We can't plug in a 0 in here. We'd end up with 1 over 0. And this is heading up toward infinity. So if this is the area below this function, above the x-axis, to the right of -1 and to the left of +1, so here's +1, we're interested in this area. Let me highlight it. We want this highlighted area from here this way Okay, so we want that highlighted area, and as you can see, around the value of x equals to 0, there's no roof on this area. It just keeps going up forever, infinitely high. So how are we supposed to find that area, right? So it makes sense that this interpretation of an integral runs into a problem there. Okay, so the moral of the story here is you got to pay attention to the underlying conditions necessary for the fundamental theorem of calculus to work. The function has to be continuous on the set you're interested in. Now, if we were interested in integrating on the set from, let's say we just came over here and changed this set and changed it from 1 to 2, if we did that, then that wouldn't be a problem, right? Because on this set from 1 to 2, the function is continuous. It's when you wrap it around the 0 that we run into a problem. If we want to integrate from -1 to 2, again, we're including that 0, and that's a problem. If you think about rectangles, right? Remember the area we approximated through rectangles. We threw in a rectangle there, and we threw a rectangle there. Eventually, we'd end up with at least one rectangle that just has an infinite height. So the area might be infinity. True? Okay. So this kind of a thing requires more thought. If I wanted to approximate this one, for example, let's go back to our negative. So our negative 2 to +1 still wraps around that 0, so we have a problem. What we could do is approximate it, right? So this would be okay. Let's do it in pieces. Let's go from -2 to something really close to, let's not do it in red. What we could do is say an approximation. Approximation. Let's do the integral from -2 to something really close to 0 so that we avoid that infinity thing. So let's make it -0.1. That's pretty close to 0, but still not 0. And then we can integrate this. Okay, so now we're not violating any of the rules of the fundamental theorem of calculus. So this is going to be a valid answer. And then that's going to give me kind of like the left half. And then plus, and then we can integrate from +0.1, that's really close to 0, all the way up to 2 on 1 over x squared dx, right? This kind of a thing is perfectly valid, and it gives you a pretty good approximation. And if you want an even better approximation, well, then let's make this even closer to 0. How about -0.001? And then this one, we make it from 0.001. Okay, even closer, you want even closer? Okay, well, let's make this -0.0001, and let's make this one +0.0001. Okay, well, you see where I'm heading with this. We can let this be a variable, and think about the limit as that variable approaches 0 from the left-hand side. So let's let it be, I don't know, how about t? Let it be t, and then we're going to explore what happens as t approaches 0 from the left-hand side. And same over here, we're going to let this be some variable. I don't know, how about the variable w? And we're going to explore what happens as w approaches 0 from the right-hand side. But at any rate, that's fun for another class. That's exciting things to come in a future calculus class. But that's not something we're going to do here. So I'm just letting you know, exciting things to come. For us, all we really needed to point out is that this does not have an answer for us. So if you run into this, just put no solution. It does not exist for us because we don't have more advanced techniques for finding the exact answer. Now, they could say, find a suitable approximation, find a reasonable approximation. Oh, okay, we can approximate it by coming up with a specific number here that's close to where the 0 is, and then finding it there. Okay. In the past, when I did this, people then just thought 0 was always the problem. It's not about 0. It's about where the vertical asymptote is, right? So if, on the other hand, note that if, on the other hand, they had given you this question, the integral from, I don't know, -5 to +5 on 1 over x plus 3 squared, dx. Well, now the problem is at -3, right? There's a vertical asymptote at -3. So the problem isn't always 0. The problem is that you don't want to divide by 0. So you don't want to plug in something such that your fraction, you end up with a fraction with a 0 in the denominator. Okay, so hopefully that's more than enough information to get started on your homework. Please let me know if you have any questions.